Buenos días a todos y muchas gracias por uniros a estos seminarios que empezamos a hacer online, esta nueva etapa que bueno, vamos a iniciar ahora y no sabemos si la continuaremos así o podremos volver a hacerlos presenciales. Y bueno, pues hemos decidido que aunque no sepamos si podemos continuarlos así o no, pero por lo menos intentar continuar la vida dentro de un orden. Continuamos con el seminario que teníamos programado cuando nos confinamos y que en aquel momento no se pudo realizar. Y bueno, pues va a ser Tiberio el que presente a Klaus Attenkofer, que es el ponente que nos va a acompañar hoy. En el chat os damos la bienvenida y decimos que al final de la presentación, si queréis hacer cualquier pregunta, la podéis hacer a través del chat y nosotros, bueno, pues se las pasaremos al ponente para que él las conteste. Y deciros que, por favor, que apaguéis todos los micrófonos y nosotros apagaremos también las cámaras para que se pueda seguir mejor la presentación. Para los que no estáis habituados a trabajar con Conecta, deciros que si queréis ver la presentación en modo de pantalla completa, abajo a la derecha tenéis una esquinita con 4 flechas y si le dais ahí, pues aumenta lo ponéis en modo presentación y lo podéis ver más grande. Y bueno, pues nada, daros de nuevo las gracias a todos y esperemos que sea una buena oportunidad de seguir conectados todos y de poder seguir con estos seminarios. Y ahora, Tiberio, pues, te doy la palabra para que lo presentes.
Thank you, Sagrario, for organizing that. I think it's we are very thankful to you and also to Jessica Roldan, who are supporting that. I think it's very important that we recovered, as you mentioned, slowly normality as far as we can. So today is really a pleasure to have by us Klaus Attenkofer, because we invited him to deliver a talk in May 2020, and for obvious reason, this talk could not be delivered, and this talk was thought to be done on presential, of course. And now, although we have not Klaus here, and this will prevent us from enjoying a lunch, but anyhow, we have the pleasure to concentrate on science, which is also the main topic of the main purpose of these events. So Klaus Attenkofer got his PhD in Hamburg, although he really studied in Munich. And he has a wide expertise in the field of synchrotron light sources. He worked as a beamline scientist in Argonne National Laboratory in Chicago, USA, for more than 10 years before joining Alba. And even before, he has been the program manager of the Heart X-ray spectroscopy in Brookhaven National Laboratory, NSLS. Some of you know this facility. It's a great facility in New York, United States as well. And most of his career has been focused in material science, chemistry, and environmental issues, with a strong emphasis in energy science, developing of new detection and data acquisition systems, and implementing different sample environment for synchrotron research. And with this, I give the word to Klaus. Thank you very much for coming, and we are ready to enjoy your talk.
Thank you very much, Gio, for this nice introduction. So let me tell you that there's some kind of feedback, I feel. Somebody must mute, I guess. So thank you very much. So this talk will be on one hand an overview about what we are doing in from the facility side itself, but also we will speak a little bit about the science, what we are doing here. So I hope I get the right mixture for the audience, that we have really interesting kind of talk. So what is Alba? So you may know Alba is the Spanish Synchrotron radiation facility. So it's a national facility. It's 50% funded by Madrid, 50% by Catalonia. We are quite international. So on the staff level, we have 27% international staff, and on the user community, it's about 35–40%, which are not coming from Spain. So we are a mixed club, and we have a lot of international collaborations and also obviously national collaborations. So to our timeline, so we were conceived somewhere around 2003 with the approval of Alba II. Then there was the construction beginning at 2006. 2012 is the big milestone of operation start. And now in 2021, we are operating 10 beamlines and 3 are under construction. And in December now, it was also recognized from our funding agencies that Alba should need an upgrade. And so it was officially started that we are doing now the planning of this upgrade. So I will first speak about Alba, and then we'll slowly move over to Alba II and also motivate this kind of change of the perspectives. If you start now with Alba, which is fully mature, you see here a few numbers. We have 220 people on staff, so we are a relative reasonable sized kind of institution. We do about 300 experiments, and this means the users do the experiments, obviously, and we help the users. We have out of that 300 publications per year, which tells you that the success rate per experiment is pretty high. And also there's about 34% is high impact factor from this 300 publications. So I think we do scientifically pretty well, and our users too, obviously. We have about 7,500 public visitors. This is also important because I think this is a really important role from these facilities to have public relations. And you see that the ratio between national and international user is about a third, something a little bit over a third is international and 2/3 are national. So if you now look closer in the program, you see that you have your user program is split up in 3 parts. The academic part, which is mixed between basic and a little bit applied. Then there's a joint academic and industrial program, which is more on the applied side, obviously. And then there is the proprietary research, which is then fully, obviously, industrial. So if you think now from a scientific point of view, what is Alba really standing for? And so we have really 2 missions. Number 1, and I start here with the lower part, we are providing simple, any kind of X-ray service, what the Spanish user community needs. That is one of our missions. But there's a second mission, and so what we want to also do is really providing solutions for much more complex problems, but now in some kind of target areas. And the 3 target areas what we have at the moment is health, energy, and sustainable innovation technology. And this is in principle spintronics and QRS. When we go now really in how we do our job is, I said it already, we provide state-of-the-art X-ray characterization tools to any Spanish user. On the other hand, we also try to develop the cutting-edge technologies, and here is both instrumentation methodologies as also the data analysis strategies. And we will speak then later much more about that, what I mean with that. And then the other thing is to make these tools, what we have to develop, really available to a larger community. And then last but not least, and I think most people would not think about that, we want to be the kind of avenue what you have if you want to connect to the larger European network in this kind of X-ray carousel. So to achieve all that, we have in principle 3 different building blocks, so tools. On one hand, we have our user program, and I said already it's a public and a proprietary user program. On the other hand, we have this training and outreach program, and then we have the in-house research program. And the rest of the talk is now showing you how these 3 things really create what I am describing here in the top of the slide. So what are our tools? So we are split up in 3 scientific areas. So life science area with 6 beamlines, 3 beamlines in material science and / chemistry, and 3 beamlines in the area of electronic structure and magnetic structure. So you will see that there are the beamlines, which is our main portfolio. We build at the moment out an electron microscopy program, which is also available as a general user program, which means free of cost. And then we have this user labs, which starts to be more and more important to get really the samples prepared in the way that you can use it in different beamlines. There are also 3 beamlines still under construction. And here a little bit more in detail what the beamlines are doing. We have an IR program, a powder diffraction program, a soft X-ray, full field microscopy, SAX works, MX, the XAFs and the powder diffraction on this bending magnet beamline, an ARPES program for band structure measurement, XAFs again, that is correlating here this NOTOS and CLASS and MSPD. And then you have SIRSE with ambient pressure, XPS and PIN, and Boreas with XMCD and soft X-ray scattering. So it's pretty much all the things what you would normally expect on a 3rd generation synchrotron. Then we build up our TEM program or EM program. And so the first user operation of the first 2 microscopes will start next year. And there is one which is focused on nanoscience, a TEM, a high-class aberration-corrected monochromatic transmission electron microscope. And there will be also FIP included. And then there is a cryo-EM for life science, and this is focusing on the particle screening, but also full data analysis. So there's a pretty nice detector system and a full automatic sample loading. So both will run in the user mode, and then most likely in 23, so this microscope, the funding was already approved. And this is a microscope which is fully focused on in situ and operando experiments. So it has an environmental chip system in it. And this chip system will be then also compatible with all the, with a lot of the beamlines what we have on the floor. So X-ray and TEM will be fully integrated. Now to the training and outreach, you see here some examples. It goes pretty far from really student schools like the Hercules School to the user meetings, the outside user meeting, to normal kind of workshops. We go also a step further, and we have a pretty important mentoring program, if you like. We train a lot of students, and this has various forms. So if you're a student, you can ask me, and I can tell you the details of that. And the next step is obviously we also reach out to the larger community, and we also organizing conferences. So this here is a conference on quantum technology. It will take place in Italy in May 22. So originally it was planned for 20, but obviously that was not working out. So we are at the moment redoing that. And I think it's a pretty interesting program which will go really into detail what is new, needed in QAS, but also what can Synchrotron do for that. And then the last part of our outreach, and I'm somehow proud on that, is our outreach program to schools, so that the youngest get really interested into science. Now let's change gear and look into the issue of our in-house program. And this is now important that you understand how our in-house program is really drilling down in these new methodologies, and also how we get this solution concept really working, and how that will go then later on into the Alba II concept in this upgrade. So we are normally focusing on 4 areas here. So multi-length scale imaging for life science, then catalytic processes, and typically it's minimizing CO2, sequestration, energy storage, obviously, and then device and materials engineering for quantum informatics and spintronics applications. So here is now an example from life science, and you may come, for example, from MX, so where you are looking for the structure of a molecule. But now at the end, you want to see how this molecule acts really within a membrane, and the membrane acts within the organelle, and the organelle within the cell, and so on. So this microscope here is a soft X-ray microscope. And the trick is that you choose the energy between carbon and oxygen. So, which means that you are absorbing a lot on carbon, but you are not seeing the oxygen. So in aqueous environments, like in a cell, you can get the contrast on the carbon. And here is a model what you derive out of such a experiment. It's a cut through a tomography image. And you see here the different organelles and the kind of resolution what you get. This is a micrometer, so you have really something like 50 nanometer resolution, and you can really identify structures of the different parts in your cell and obviously the organelles. So this is, for example, a work where they studied the changes in a neuro disease, and they look for the kind of changes of the membranes. Now let's go a step further and really look how you get to this kind of picture and how you do the science out of it. So here is an example where you are studying the uptake of an iridium compound, which is used for cancer therapy. And the question was, does the iridium goes really in specific organelles, or is it distributed all over the cell? And obviously the impact on the toxicity is hugely different how that is done. And so what you're combining here is, in the first step, you do this kind of fluorescence optical part to understand where is the individual organelles and which are really activated and which not. In a second step, you go on another probe and you're measuring with fluorescence where the iridium is situated in the cell. And then in a third part, you will do now an overlay between this pattern and that pattern, and you get to this image. And now you use this soft X-ray microscope, identify really each individual organelle with high resolution, and you compare this with this image. Out of the 4 images together, you end up with that part here, which tells you now exactly which organelle and which kind of material you have in the cell. And when you drill in and compare with the fluorescence map, you can now identify here a mitochondrium, and you can see that all the iridium is within the mitochondrium and not outside. So this is extremely important to know. And this is obviously what you need to optimized to get this cage right, so that the uptake is optimized. What you see is, to get at the end to this picture, you need a multimodal imaging approach, and these are over multiple length scales. And on top, you have the problem that you have the issue that you have to be statistically relevant. Oops, sorry. So if you now try to abstract that, what we have learned now is what we need to do in such a complex environment is, first of all, we have to combine multimodal imaging approaches. The second part is to align everything and to do the tomography and get the individual modes of imaging overlapped. You need data analytics. And at the end, you have to provide all the experimental expertise and the facilities to prepare the sample and optimize your processing. Now, if you go now the next step and say, okay, if you go away from life science, what can we learn now, what we need to do? And there are three things. So on one hand, the grand challenge is really imaging from the smallest building block what you have up to the largest unit. What we had not seen in this example before is how we get now the molecular structure up in this picture. And this is exactly one of the kind of things what we are trying at the moment here internally to get to, and with our partners to make new methodologies to do that. Providing statistically relevant information, obviously, that's really important. Not only a single cell, but it has to be the whole unit of a tissue. And then understanding the structure-function correlation, at the end you have to understand how this iridium now really destroys the mitochondria and how is the reaction process within the cell, and what are the unwanted processes in the cell. But these three things are very general, and you can apply it now through all the other examples what I will bring. Here is an example from a battery. So it's the charging and discharging of a sodium, and this is a oxygen battery. And so during the charging and discharging, what you are doing is you're changing the oxygen concentration in this cathode material. And you can now measure this oxygen concentration. You can also analyze what kind of defect structures you really create. And at the end, you can cycle it, and you can see which are reproducible and which are not reproducible. And everything which is not reproducible, obviously you get into trouble, because that is degradation of your battery. So this is, for example, another direction where we are going. And now we are stepping one step back, and this is another kind of problem, what you see often in catalysis. So you have a very messy system, which is something amorphous or nanocrystalline, and you know that the exact defect structure is most likely the part which is really determining if your catalyst works. And your problem will be to image this structure. And it turns out this is not trivial, because most of the standard imaging processes are not working, because it's a statistical issue, and you have to really understand how you describe a amorphous structure. And so the problem is, can you now use a spectrum and get out the structure? We know that when we have the structure, we can calculate the spectrum. But the reverse process is not known. So the good message is, yes, you can do that, but it's not so trivial and perhaps not very obvious how you think it is working. So the first step is you are going in the database and look. So this was a titanium oxide catalyst. So what we are doing is we go in the database, look for any kind of compound, what you can find with oxygen and titanium. And then we are calculating all spectra for each side of this different compounds. And after we have that, we are thinking about a metric to measure how well our model is describing our data set. And besides the metric, what we need to find out is also a descriptor. So in the easiest way, a descriptor would be in that case, for example, how many neighbors has my titanium? Is it 6, 5, or 4? And then when we have decided these two things, we go here in the next step and we take all our calculated data and split it up and see if it groups in the right way. So if it groups in the right way, we have a decent descriptor and a decent matrix. The matrix is something what we have to refine, and I say just why. Now we are measuring a bunch of materials, what we know that it works, and so we are now applying our mechanism on this data set, and we will see that parts of the data can be reproduced, and we may get the right material out from this part, or we may not. So some will work, some will not work. Now we have to understand why it's not working, and for that we have to understand what is in the calculation not right, and what is a systematic error in my measurement. And after we have understood that, we refine our theory part and our measurement part, and it may be also that we have to change the metric. And now we go again through, and we do that until we can really describe all important parts in our spectrum. So if we put all together and try to say what we have really done is we combine these three boxes here to get the structure model. So on one hand, we have the imaging techniques. On another part, we need ensemble averaging techniques. And on the third part, we have the simulation part. In the simulation part, we have DFT and other kind of ab initio calculations. We have the data analytics, which turns out is an important part to make really sense out of the data. And then we have the structure and data reference databases. And our data here will go in this database, but also the databases what exist go into our measurement concept and plan. All these measurement tools are relatively fast and easy measurements, and we can do many samples, and we can do also automatically many ensembles within the sample, whereas this part is difficult and takes a long time and has only very few samples what we can measure, but we need it obviously to inspire here the right modeling, and on the other hand also get to an idea about if our final structure is really the right one. In this process, we have learned, however, more than only the image. We have understood, because of this calculation, what each individual structure or element of the structure has importance to the function. And this is now the next step. So how is the function part? So this is an operando experiment of a battery. So you charge and discharge the battery, and you look here on a specific peak, and you see how the lattice is reacting during this charging and discharging of the battery. So you change simply the lattice constant, but on the other hand, you may also do phase transitions. So all that is what you see here. And you see if the battery comes fully back to the original material, or you have strain stress, which is left over. So now we switch gear and we go to magnetism. So here is a skyrmion. This skyrmion is this hedgehog-like kind of distribution of electron spins, and one of the kind of ideas how we can do some kind of QAS in future. It plays also a really big role in spintronics. And so this structures are not very large, and you see here it's about 500 nanometers, this thing. So you need a high spatial resolution, but you need also magnetic contrast. And you see here in PIN, one of the instruments, we can really measure this distribution of the spins. And you see here the vortex, how it develops under different external conditions, and which is this center part. And then how the vortex is excited within this whole structure. And so you can now start to study the whole excitation process. But you can go one step further. So when you go now here in something like a nanorod, so it's here a kind of a nanowire with some kind of chemical composition changes, and you're asking, can this chemical composition change pin the magnetic in the wire, and what is the structure of the magnetic moment? And so on the surface, you will see only the surface electrons from the wire, because the inner part simply cannot get out, it gets scattered, so it doesn't contribute. However, through the wire, a light coming through, and there will be a shadow behind the wire, and this now measures the full thickness of the wire, and you get a geometry that you get a higher resolution. So you can now look here inside the wire and see really what is the different magnetization, and you see here exactly that thing. This is the transmitted beam, and that is the beam itself. You see the dark and bright contrast is different between the two, and that is exactly the magnetic contrast what you have. And when you do that, you can then come back and compare it with your original kind of models. And this model is exactly right, and depending on the thickness, you get a totally different structure, as you see here. So another of imaging, and you know that, is holography. And so you can do that also with the X-rays. And so what you're doing is you have here your sample on a wafer. Here is the sample, and you build also a pinhole here in it. And if you illuminate the whole thing with a homogeneous coherent beam, you get a speckle. And in principle, it's the same speckle pattern what you get when you do what is it called, a normal hologram, a laser hologram. Use the reference beam to read it also out, and now in our case we take this pattern and do a mathematical retransformation, and then we get the image. Something like that you get down to the nanometer and sub-nanometer resolution. You see now we have all the tools from the subatomic resolution with the TEM to the different kind of imaging tools, and all the kind of tools for the ensemble averaging, so that we can get really a full picture. If we want now to understand really the structure-function correlation, what we need now is we use our original structure model, we plug in the operando techniques, do again the ensemble averaging, the data analytics, and the DFT, and we do the imaging, and out of that we can identify what kind of part in your structure is responsible for the function, and which of the structures are changing but don't relate really to the function, but are more related to degradation and some kind of defects. So out of whatever reason, my here goes always out of the full screen mode. I hope I don't screw up the talk for you guys. And now let's go a little bit step back and think about how that all what I told you now is correlating for the future of Alba. And this is now really this Alba II. What is the vision of that? It's a fourth generation synchrotron. And for these branding areas, what I introduced at the beginning, so health, energy, and the sustainable information technology. So if you drill into that, what you can now do for these areas is you are providing now all these enhanced imaging tools, and you prepare all the methodology to do the multimodal imaging for these areas. Then you do optimized throughput instrumentation. You create all the data handling facilities and obviously the connection with the big data so that you connect it also to industry. And you provide all the simulation and data analytics parts. And then obviously all that cannot be done only by Alba alone, but what you need are strategic partnerships. And this Alba II will be connected strongly with larger partnerships. And CSIC is, for example, one partner, which is a very strong partner of us, with some activities already now, but this will grow. And these partnerships will now create a lot of the additional tools what you need. And obviously, we will still do, if you come for a single experiment, simple your single experiment. So there will be no change. Now, one thing is important, and unfortunately, there's not everything what I wanted on this slide to show you there. But for getting to Alba II, we need you. We need your input. And so there are two kind of processes which are going on. So one is we have to decide on the science case, and we have to build out really good contacts that we develop the right synergies of all our tools. And on the other side, we need also obviously to develop the beamline or the instrument proposals. And so we have here two different blocks. And one thing is this kind of science case is the colloquium. So I invite you to look also on this link. So really quite interesting talks. They are all recorded, or most of them, so you can see the recordings also. Then we have a workshop program, and both the colloquium as well as the workshop program, please contribute either passively or actively on these programs, and you will find a lot of interaction possibilities. And then we have something which is called the section reviews. In that we do, in principle, a SWOT analysis of our strategy and also develop a gap analysis. So with all this kind of information, we will create then at the end the science case. On the other hand, there are the instrumentation proposals, and there was already an internal concept call. So this is a kind of a dry run for the real one, which is from the users, and the final kind of proposals which will be selected has to come from the user. But here we looked already what we are missing on the science case here. And so the third part is the strategic partnerships. So if you have any ideas for that, so we are very open for any kind of ideas. Here you see some of the workshops which are at the moment in preparation. So there are really a lot of them. And you see here a timeline. And an important thing for you, maybe this Alba II workshop day. So this Alba II workshop day, there will be a lot of interactions. It will be digital, unfortunately, but this is where you get information, but also where you can put information in. And then we have, on the other hand, short after that, beginning of July, the call for proposals. This will be really something which is very easy and invite everybody really to participate in that. It should not take you much more than 2 days or so to write this kind of concepts down. It's on a very, very high level. And then we will sort out these concepts, look what fits together, and encourage then different teams to work together and partner also up our own people. And then we will develop over this time here to November the full proposals from about 3 to 4 proposals. And then we will have here the first selection of the beamline, and this gets started to be built in February. And you will see that all this kind of activities for the science case will end what we call a white paper. And this white paper will be, in principle, the guidance for creating the external reviewers for the rating, giving them a guidance what is really needed. So, summarizing, I hope that you got the impression that Alba really welcomes any suggestion and involvement of the user community, number one. Number two, Alba is really open to strategic partnerships. At the moment, they are mainly located here in Catalonia. However, this can be always extended, so don't be shy. And we simply need to speak about what you think so that we can see how that matches with the program. And then specifically, Alba is really welcome your input and engagement in the development of Alba II itself. And you have seen there are many, many things which are going on. So please contact me if you have any question, or also Katharina, here's my email. So feel free to ask any questions. And if you have any questions, please let me know. So how we do? 45 minutes. Okay, not too bad.
Okay, thank you very much, Klaus. Very interesting talk. So, as we mentioned, if you have a question, you can write it down. I mean, write down in the chat that you have a question, and we will give you the possibility to start. Just to start, I will ask you something about, because you mentioned about Alba II on beam lines and so, but what about the ring? What are your plans to improve the power of the ring? Are you going in direction achromat optics or more insertion devices? What is your situation right now?
So we are in a relative early stage, but it's pretty clear that we want to get in the I should perhaps start a little bit from the beginning on. So we are at the moment in a 4th generation synchrotron, and what we want to do is to go to what is called a 4th generation synchrotron. A 4th generation synchrotron is determined by the fact that you are diffraction limited in the source size from the X-rays. So this is not through the whole spectrum the case. And so if you're getting better and better, you go to higher and higher energy, what you are diffraction limited. So from the constraints what we have, which means the size of the ring, we can now obviously optimize our magnet structure and our electron optics. And if we put all that together, we think we can get down to something perhaps 50 picometer or something like that emittance. And this is most likely getting us an advantage in the area of, let's say, up to 12, 14 kV. I would expect that our coherence contribution is really, really high. And what happens is that the beam sizes are really collapsing, and mainly in the horizontal. So if you have now beam sizes of hundreds of micrometer, you can expect on such a source that you will have typically beam sizes of something like a few micrometer. And nanometers are relative okay to achieve. So there will be also nanoprobes. The other thing what happens is that the spectrum is, if you don't change the energy of the electrons, the spectrum gets harder. So we may reach the 20 kV with a significantly increase of photons. Not sure if that is the answer what you wanted to hear.
Yeah. It's okay. I understand. Now, with Klaus, we have a question proposed by Juan Velasco Bellet. He asks, what makes Alba, or what will make Alba II unique, special in comparison to other facilities in the European Union or in the world?
So I guess that is a tricky question to answer, right? So I would say, it's always the people, right? And the people makes a strategy. And in principle, the tool set, what you can invest is more or less similar, but how you put the tool sets together to really address the problem which is of interest, and not only that, what you can measure, I think that is defined really by the people and by the teams. And people means in that case not only the facility people, that is exactly the collaboration between key users and the facilities. And I think this facility, which will make this process really good, will be the kind of part which is really pushing ahead. At Alba specifically, I see the magnetism area as one of the really flourishing part. I think in the multi-length scale imaging part, together with MX, if we combine everything with strategic partnerships in the right way, I think we will be all excellent, and I would claim that we can compete with, at least in some areas, with people like Diamond. And then the other kind of part where I think where we can do really well is in the high throughput part and in the big data area for things like batteries or for energy storage, but also for catalysis. So in that kind of area, I think you can get really, if you have the right target, you can really get the foot down and simple provide as the first and with the best quality the services what people really, really need. I have seen that also in my last beamline in Brookhaven. It was exactly the same thing. If you provide at the right time the service what people really need, that's where you are running far ahead of the competition.
Okay, thank you, Klaus. Aurora Nogales has another question, which is the following. What type of partnerships are or will be established with groups, with whole institutions? The partnerships are specific for particular topics or are general collaboration agreements?
So this is something what we are experimenting, and obviously one has to be very careful with the partnerships that it's not supporting only one user group, but it really benefits a full user community. And I think this is one of the kind of main criteria. An example is at the moment we are building up a battery lab here together with ICMAP, and the funding is fully from CSIC. It's a proposal. And so what we are doing is really to build up for the user communities together this battery lab and also staffing it together and getting all the goodies in what you may want to have. But that brings Alba, again, a step higher, really, on that what you can do. If you go nowadays, for example, to APS, where they have a really strong battery program, you would have a full battery lab with even a lab which is doing all the combinatoric for you for the cathode material. So you can see that this kind of infrastructure is really forming a lot. Then how general it is, I think it depends really on the amount what you invest. And it's also a question how targeted the problem is. So in general, I would say there has to be a compromise. If it's too wide, it's most likely getting really difficult. If it's too narrow, it is perhaps not important enough for a large enough community.
Thank you, Klaus. We have a question by Breogan. The question is the following: how do the companies can access Alba through a usual proposal?
So there are, I think, 3 ways how you can do that. So the first thing is if you publish what you want to measure, and many companies do that, also big ones. So they contribute simple, they write a normal proposal and they are using an important effect, what they want to understand, and then they simple make basic science, but they don't tell you why they are interested in fact. So in catalysis, that's a very, very common thing. The next step is that you are paying simple for the beam time. So if you want to, typical thing is drug development. So if you have a new structure, you want to measure the structure with MX or with cryo-EM, and now you get the structure, and obviously you don't want to publish that because that's what your patent is. So in that case, you have to pay for the beam time, and it sounds a lot. It's about $500 an hour. However, it depends how big is your throughput. And for example, in MX, we are trying to push really high throughput on one of the beamlines in number 2. And so you can think about that you may get down to about 100 samples what you can measure per hour. And then suddenly the $500 goes down to $5, and that is obviously reasonable. And then there are a bunch of programs which are from the European funding agencies, but also from Spanish funding agencies, where they specifically support companies, especially small and medium-sized companies, but also startups, where the grant pays them the access, and then they can do their IP, and they don't need to publish. So I think that's the 3 ways, and we have a pretty active program. I can bring you in contact with Alejandro, who is running the industrial program, so he can give you also a hand into different things if that is needed.
Thank you, Klaus. Maria Jose Garcia Borges has a question, which is the following. The request of beam from companies is not very large, and the question is, do you have any initiative to enhance their participation?
Yes, many. So I have to say that it sounds not very much, but in reality, Alba is not bad at all in comparison to other synchrotrons. And this is correlated indeed with a very intense outreach program. And what we are doing, for example, now in the upgrade discussion is I integrate fully the industrial program in our gap analysis. If you think about, for industry, often the price what you pay is obviously that what is important. So the hour price of an hour we cannot change. This is simply our cost. But what we can change is how many measurements we are doing in this time. And so we are pushing very hard that we have some core technologies where we know that there's a user community, where we go really specifically on the instrumentation also and optimize. On the other hand, Alejandro goes really to the individual kind of areas and really explains what synchrotron can do. And then we do obviously pilot projects and all the other kind of things what is necessary to really figure out and minimize the damage to a company if something is not working out.
Thank you, Klaus. And most likely the last question proposed by Maricruz Garcia, and the question is the following. How many new beam lines do you expect to build up in Alba II? Will you support beam lines in any special direction, or only related to the main scientific areas that you mentioned, or, for example, related to small beams or coherence techniques?
So I'm a little bit surprised about the question. So because obviously you do coherence and yes, you do small beams, but that is all applied also to these areas. So I think the tools can be applied to anything what you want to study. What you will find out is that these tools are rather complex and the sample preparation plays a huge role. So it's very labor intense and you have to understand for each new area really what you have to do or not to do to be successful. So at the beginning for this complex experiments you have normally a high failure rate. And because of that, it's important that you have some areas which are settled and you really know how to do it. This does not mean that you don't use this kind of tools also to other areas. And this is what I said in the talk. Yes, obviously, you serve everybody. If you come with any kind of problem, you will get service for this problem. However, we may be not able to do, for example, to develop all the pipelines for your specific problem. And this is something where we have to understand how much we can invest on our side for this, or how much you invest for that. And we may be able to get also to a partnership depending how big the field is. So we are very flexible on that. How many beamlines we build? So we distinguish at the moment between short beamlines and long beamlines. A short beamline is a beamline which fits on the floor. A long beamline is outside the building, the end station. And if you know Alba, there is the campus what we have, then there is a small ravine next to us. And then on the other side, there are some fields. And in these fields, there will be the end stations of 3 beamlines, of the long ones, and they reach between 120 and 60 meter lengths. So these are the kind of beamlines where you would think about nanoprobes. So with beam sizes between 10 and 50 nanometer max, and most likely more in the tender and hot X-ray, but also it may be in the soft X-ray, it depends. And then these beamlines will be also beamlines which have very specific sample environments. So for example, we are thinking about that the biological oriented long beamlines may be integrated directly in a P3 environment so that you get there really from human tissue down to really some kind of virus and whatever kind of stuff to measure. In material science, there's discussion about clean room and there's the other discussion about dry room, depending in which direction you want to go. So there are at the moment lots of discussion, and if you have some idea, please come and participate in this discussion. Then there's one beamline, which is a medium kind of length beamline, which will be more in the order of 60 to 80 meter. That will be more a beamline where you don't need most likely the full length for the optical path, but a beamline where you need a very large or separated end station. So you can think about, for example, inelastic scattering is one of this kind of toys which need very large end stations, and you would not have the space on the floor, but you could do it there. And then there, as I said, there is one ID line of the short ones, which we have to decide, and this is this beamline 14, what I said. So this will be really important to get the right ones, that we get the portfolio right. So this beamline will be built relatively soon. And we think that we will get 8 bending magnet beamlines, which are quite specific, so they will be most likely on a superband. And the first calculation and the kind of experiences which come also from ESF is that this superband, they have 3-pole Wigglers, but these bending magnets with the beam quality what you have on a generation seem to be much better than a bending magnet what you have nowadays. And so it seems that this will be a very, very important point in the portfolio mix, because they can then support the programs on the individual ID lines, and they may take up a lot of load on these lines. The other thing is, with the upgrade, we plan a 2-step upgrade of all the existing beamlines, which means in the first step, you bring the end station capability on the top of that, what you would do in a 3rd generation source. And in a second step, you bring then the ID plus the photon delivery system to a point where you have a phase wavefront preserving optics. And this gives you the coherence plus the really tiny beam sizes. And this will not happen, the 4th generation upgrade will not happen to every beamline, but I would expect to all the hot X-ray beamlines. I don't know if that answers the question.
I think so, Klaus. Thank you very much. I see Maricruz. Thank you for the answer. So I guess everything was well explained. So with this question, we come to the end of this event. I thank you once more, Klaus, for this wonderful talk. I hope, and I am sure it will trigger many new proposals. And I would like to thank again. This will overload you, probably, but I think this is the idea. Yeah, I thank again Sagrario and Jessica for outstanding support. It was great, the organization, and of course I thank you all the attendees. Thank you really very much for your valuable times. I think we appreciate this very much. And I hope to meet you again in our next event. So have a nice day and take care. Thank you very much. Bye.
Thanks a lot. Ciao.
Bye. Gracias a todos por asistir y muchas gracias. Thank you, Klaus, for your good presentation. And thank you also, Tiberio, for support us. And, bueno, muchas gracias a todos y, como ha dicho Tiberio, os esperamos en el próximo coloquio, ya sea bien online o ya sea presencial. Muchas gracias a todos.
Chao.
Chao. Adiós.